Hello.
Good evening, sir.
Hello, sir.
Good
So,
evening, good
voice is
evening, sir. Good
audible?
evening. Yes, sir,
Yes,
sir,
sir.
you are
Good, very
audible and
good
good
evening.
evening, sir.
Okay, good evening, sir. Very
Okay,
good. How are you, sir? Fine?
okay, sir, fine, sir.
Hmm. Okay, sir. Have you gone through all the lectures? Week 8?
Some of this, actually, I could not understand actual lectures, sir, because uh, I, I could understand whatever you are teaching and you and another TA. But
Okay,
it
okay.
has been the problem, sir, from the lectures.
Okay, okay.
Okay, even though no problem, sir, I could understand your thing. Okay, sir, another
But,
has attended. Thank you, sir.
okay. Okay, let me share my screen.
Okay, sir. Okay, right, sir. Thank you.
So, in this lecture also, we'll deal with some, all this, whatever the question we're going to solve. I'll just give a MATLAB how you can able to see the response. Okay, so I am able to access my system through MATLAB. So if any problem you are unable to understand, then you just tell me. Otherwise, this part of the lecture mostly, uh,
Sir, as per our exam, is MATLAB compulsory, sir? I think it
I don't
doesn't.
think MATLAB will be there because
Yes, sir. Yes,
in
sir.
the system
So
actually,
better it
you see,
solve some problems
MATLAB
and
will be
stuff.
not accessible. I'll
Yes, sir.
solve
Yes,
the
sir.
problems, but I will also show you how the response will be. Means
Okay,
in
sir.
every
Okay, 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 okay.
that
Right,
but
sir.
means
Thank you.
if you want to try whether our answers are matching or not matching, then you can verify that.
Okay, sir.
So this part of the lecture actually week 8 is mostly related to designing of the compensators. So in the last class we have gone through various kind of compensator like lag compensator, lead compensator. So now we are going to design our system by using this compensator. Okay, so in the root locus domain. Okay, so because week 8 is mostly dealing with time domain analysis, from week 9 onwards it will be frequency response analysis, how we're going to design the compensator by frequency domain analysis. But here we are only focused on the time domain approach, how we are going to design our compensator with respect to the plant so that we can reduce the transient response as well as we can reduce the steady state error. So mostly in the last class, just I'm giving an overview of this you can design by the lab lead compensator. This is the block diagram. So in the course also it will be there. Means how Sarah has also taught that this diagram helps us to find out the transfer function of a lead compensator. How we can do that? So we can mostly do just find out the transfer function. Transfer function is nothing but the output by input. So first, uh, is my screen is visible right now?
Yes, sir. Yes, sir. It's visible.
Fine, right. Just let me check. I started the recordings or not. Yeah. So you need to find out the transfer function. So transfer function is nothing but output by input. So if you consider that this is a network, which is combination of the R and C, you can replace this by C. You can replace in Laplace domain by 1 by C1s, and with that one R is connected in parallel. That is R1. I am saying, and here this R2 is a constant. This in frequency domain will be R2 only. So and this V0 it will be V0 S in Laplace domain, and this input is V in. This will be V in S. Okay. Now how to find out the transfer function? This is just a representation of R. Let's imagine that this is Z1 and this is Z2, and you are giving some input here V in, and you are giving some output here V0. So just apply voltage divider rule. Voltage divider rule is nothing but V0 S divided by V in S is nothing but Z2 divided by Z1 plus Z2. So if you solve this, okay, and put Z2 equal to R2, okay, Z2 is nothing but your R2, and combination of Z1 is nothing but R1 parallel with 1 by C1S, okay. Someone wants to join, let me add. Yeah, Ganesh, any doubt? Have raised your hand.
No, sir. Thank you, sir.
Okay, fine. So you just find out Z2 and Z1, then put in this formula. This is just a voltage divider rule, and find out V naught M by V naught S. Just I'm writing out the direct formula. So you just calculate by yourself. Okay, so this will be R2 divided by R1 plus R2, and this is a constant which is multiplied here, and here you'll get 1 plus SC. Okay, C1 here R1 divided by, and this will be 1 plus S times of C R1 R2 divided by R1 plus R. Okay, this is the overall transfer function. Okay, but you know that time constant in RC network is RC only. Okay, R into C combination. So if I replace this value, then R2 by R1 plus R2 will be there. Then it will be replaced by 1 plus time constant. Let's say R1 C1 is T1. I'm putting here T1 divided by 1 plus, this will be this R2 by R1 plus R2. This I'm calling at some constant alpha. Okay, so in place of R2 divided by R1 plus R2, you write down alpha. Okay, so here is a term R2 divided by R1 plus R2 is there. So that will be also it will be uh, your alpha term, so it will be alpha times of, and here you can call the time constant again R1 and C. So this C is nothing but your C1 only. Okay, so here you can say alpha T1, and the term is S is there. So this is your transfer function. Okay, so this is the overall transfer function. Okay, V naught S divided by V in S. So why I'm deriving this formula, because you know that this will be helpful in designing our compensator. Okay, so let me clarify that here in this case alpha is less than 1. I told you in the last class you can represent your lead compensator transfer function either by 1 plus st1 divided by 1 plus alpha t1s, or the reverse also. It depends upon the alpha value, whether alpha less than 1 or alpha greater than 1. So now, similarly, if you draw the Bode plot like this, okay, if you do the Bode plot of this will be like a high pass filter. I told you in the last class. Okay. So this is a high pass filter. Okay, and this gain is defined by some. We'll find out. This will be 10 log 1 by alpha. Okay. So 10 log 1 by alpha. This magnitude, this distance from here to here. So this will be 10 log 1 by alpha. So whenever you design your lead compensator, your alpha value should be, if alpha is less than 1, okay, if alpha is very very less than 1, then this value is going to, m value is going to be very very high. So always what you do, you have to keep your alpha is less than 1, but it should be close to 1 such that this m value is less. Okay, as m value should have to be less for the proper design of the compensator. That is described in the lectures. Okay, just I'm giving an overview that how you select the alpha value. Alpha value is less than 1, but it should be chosen in such a way that it is not far away from 1. It should be very close to 1. Okay, so now uh, this is the Bode plot. Okay, so similarly lab compensator, you can find out the transfer function. Okay, so transfer function is nothing but P naught S divided by V in S. This is represented by this circuit diagram. This is the lab compensator general block diagram. It's by using passive network how can you design your lab compensator. So similarly you find out, okay, this if you take this your Z2 and this one is your Z1, then again it will be Z2 divided by Z1 plus Z2. Apply voltage division rule and find out the transfer function. This transfer function is again in the form of 1 plus Ts divided by 1 plus alpha Ts. Okay, so again alpha equal to here. If you calculate the transfer function, you will get R1 plus R2 divided by R2. As you can see, this value is definitely greater than 1. Okay, because this is 1 plus R1 by R2. So that value is greater than 1 because R1 and R2 are both positive. Okay. So here in both lag and lead compensator, if you find out the Bode plot of this one, you can see this is a low pass filter. Okay. This is a low pass filter. Again, this height is again 10 log 1 by alpha. Okay. So here is alpha is greater than 1. You should have to keep this value as low as possible. This height, always this height you have to keep. So if I denote this height as m, that will be 10 log 1 by alpha. Okay. So this value has to be very low, then alpha value should be greater than 1, then this value alpha should be far away from 1. So this value you have to remember that how you choose your alpha in the design of a lead compensator and lag compensator. Not only lead and lag compensator, but also in combination of lead and lag compensator, how we are going to design the compensator. So that is very, very important. So let me go through some of the examples to better clarify how we are going to design. Okay. So let me go to question number 1. So the question number 1, this is given. You just see, forget about GCS for now. Just assume that this is a plant. Her transfer function is given. So let my plant transfer function is 1 by s into s plus 0.5. Okay. So this is the plant transfer function. Once you have a plant transfer function and you read the question what is given, you have to design, the aim is to design a lead compensator, which is GCS. Now GCS is coming into picture such that the damping ratio zeta is 0.6. So he has given your zeta is 0.6 and the undamped natural frequency omega n is given, which is 0.8 radian per second. So these two values which are given, these two values are for the overall system, including the controller and the plant. So if I write the whole transfer function, then the transfer function is nothing but GS into GCS. Okay. So this is your total transfer function and it is now having a unity feedback system. This is a transfer function having a unity feedback system. So it means the closed loop transfer function will be G of S into GCS divided by 1 plus G of S into GCS. So for this closed loop transfer function, these two values are given, zeta and omega n, for the overall system is given. Okay. So now first, to find out the overall transfer function, we need to find out this GCS is what? What is that GCS? Okay. So you have to find out what is, whether it is a combination of only uh, okay, in the question it is given a lead compensator. Okay. So lead compensator means you have to think that in the last class we have discussed that lead compensator means addition of a zero. Either it is zero at the origin, but if you add a zero at the origin, then practically actually this value cannot be implementable. So that's why you are adding some zero value which are very close to origin. It means, and my point is that you are making a lead compensator, means you are adding a combination of pole and zero. So that zero, it can be placed here. This is the lead compensator. Okay. Because some proportional value is there. But this, if you add a zero at the origin, then this practically this thing is not implementable. It cannot be designed that system. Okay. So what you can do, you this shift this zero value somewhere very close to the origin. Okay. Somewhere very close to the origin. You know that when lead compensator, your phase is always positive. Okay. But phase is positive means this zero is now shifted to here. Okay. It is very close to origin and a pole will be there. Okay. So one pole will be there here. So this total combination is nothing but a lead compensator. So last class we have discussed that how a lead compensator pole zero location. So let's say this is 1, then this is be 2. So not this is 1, this is some point 1, you can say it is very close to the origin. Okay. So in that way you have to design your lead compensator so that why we are designing the lead compensator, so that you need to have a fast transient response. We can reduce the peak overshoot, but the point is that whenever you have adding a zero, your steady state response does not affect it, but transient response improve. Improve means your peak overshoot is increased, but you have to design the pole and zero location in such a way that that overshoot also reduced. Generally, acceptable overshoot range is something less than 10% or less than 15% maximum. because we cannot design a system which having a step response where peak overshoot is going there more than 20%. It is not acceptable. So this percentage peak overshoot value is either less than 10% or less than 15%. That is an allowable range for the system. So keeping in mind that you have to design a system, but in the question he has given some data. Maybe he has given percentage peak overshoot, maybe whatever. But in the question they have given the damping ratio zeta and the omega n value. So let me solve the approach. How you can going to solve the question. So these are the questions. Some 10 question I have taken for this particular transfer function. You just note down the transfer function 1 by s into s plus 0.5, and a GCS is a lead compensator we are going to design. I need to solve all the 10 questions. So the first question is that find the real part of the dominant pole. Find the real part of the dominant pole means first you have to, this is a second order system, because it is given 1 by s into s plus 0.5. Okay, so our standard second order system is generally represented by omega n into s plus 2 zeta omega n. This is standard second order system representation. If you have a unity feedback system, then the total transfer function is something like that: omega n square divided by s square plus 2 zeta omega n s plus omega n square. Okay, so for this value, you know that if you solve the denominator part, I'm going to the next slide. Okay, let me come here. So this will be omega n square divided by s square plus 2 zeta omega ns plus omega n square. This is a total transfer function, cs by rs, you can say output by input. Now if you solve the denominator, the characteristic equation s square plus 2 zeta omega ns plus omega n square equal to 0, then you have to get some, there are two roots because the second order system, one is s1, another is s2. So s1 is something minus zeta omega n plus minus j omega d, or s2 will be minus zeta omega n plus, if it going plus, then give it minus n j omega d. Omega d is a damped frequency of oscillation. Omega d is called a damped frequency of oscillation, which is nothing but omega n into 1 minus zeta square. This is the omega d value. So for the system what is given, your zeta value is given to you. What is the zeta value is given to you? How much? The zeta is given zero point 0.6 and zero point 0.8, right? So now zeta is zero point 0.6, omega n is given zero point 0.8, right? So this is given to you. So if you can solve this, if you put in this formula, you can find out omega d value. What is omega d? Omega n 0 0.8 into 1 minus zeta square. Okay, so what is your omega d? Whatever the value of omega d will get, then you have to first define what is s1. S1 is minus zeta omega and multiply these two. So 0 0.6 into 0 0.8. So this will be 0.48, but with a negative sign. Okay, then plus j omega d. If you put in this formula, you will get some omega d value is 0.64. Okay, so now this is your s1. Similarly, s2 will be minus 0.48 minus j 0.64. So how, without putting this omega d, these two value in the omega d formula, can you able to find out the omega d without putting this formula? You know that whenever in the root locus or in the second order system, the second order system, if I am considered this my origin, then this circle having radius omega n. Okay, because with these poles will be always moving in this circle. So when suppose a complex pole will be here, it will be move here like this, and here to be coming like this. At this point, these two pole will be meet, and after some point, they will be separate away. One is going to the right, another is going to the left. So this is the root locus generally plot. Okay, so you know that this radius, the circle radius circle hota hai omega n. So this is omega n. Okay, and what is giving zeta? Zeta is nothing but this. If this is theta, then theta equal to cos inverse zeta value. Okay, theta equal to cos inverse zeta. So from here zeta you can find out theta. And okay, then remember that always this is a triangle. This is because if I am saying that this is minus 0.5, let me assume an example minus 0.5. plus j uh, 0.7. Okay, so this is always a right angle triangle, because if you take the square of this, means if I am saying that this is a, if I apply a Pythagoras theorem to this value, okay, this is just a right angle triangle, nothing is there. This hypotenuse is nothing but omega n, this value is minus zeta omega n, and this value is your omega d. Because why I'm calling this height is omega d, omega d is a damped frequency of oscillation. It means when the pole is at this location, then you get a critical okay, critical stability condition. Critical stability condition means, I told you the definition of critical stability means the poles will be oscillate at a constant frequency of oscillation, and that constant of frequency of oscillation is called the damped frequency of oscillation, that is omega d. This omega d is called this pole location, when the pole is located at any point on the imaginary axis. Okay, you consider this is my origin. On the left hand side the distance is zeta omega n, and this pole will be located at omega d. If you find out the hypotenuse, then minus zeta omega n square plus omega d square, that will be always equal to omega n square. It means if it is omega n, if this is minus zeta omega n, this will be omega d. This is not a Pythagoras theorem. If this is 6, and you know that in a Pythagoras theorem, if this value is 6, this value is 8, then this value has to be 10. Okay, to satisfy the Pythagoras theorem. Okay, so that's why if it is 0.6, it is 0.8, then this value has to be 0.8 square minus zeta omega n square. So you have to find out from this, okay, by drawing the triangle. Otherwise, if you remember the formula also, you can find out what is omega d. This omega d value is 0.6. Okay, so there are two approaches I told you. So now after finding out this S1 and S2, okay, so which one is dominant pole? The dominant pole, you have to understand that which one is the dominant pole. One pole which is minus 0.48 this point and here. So one pole is located here, minus 0.48, and another pole is, okay, so this is positive and this is a negative, because they are complex conjugate. So always take the positive pole. Okay, so always you, whenever you're solving the dominant pole concept, designing a compensator, always choose this positive pole. So the positive pole I'm interested is now in S1. So this S1 is my dominant pole. Okay, this is a dominant complex pole, because without compensation if you find out, okay, without compensation if you find out the transfer function, okay, then I'll show you that how you can draw it in root locus approach in MATLAB, how you're going to solve it, okay, without a compensator design. But with a compensator design, okay, so whatever till now we have calculated, this is the total system transfer function dominant pole, because I'm calculating for the total system transfer function by using the value which is given in the question. Till now, any doubt till now how we have calculated dominant pole? See, I am going a little bit fast because all the things I have covered. Time response analysis, root locus. If you have followed my lectures, then I don't think it is a problem to tell me that which is a dominant pole. How can you find out the dominant pole? I have not done anything. I am just using the data which is given in the question to find out the dominant pole. Zeta is given, omega n is given. You just find out omega d, or you find out what is S1 and S2. Out of S1 and S2, take the positive pole, and that pole is called the dominant pole. So that's it. Nothing is there. Clear my point?
Yes, sir.
Right. So now in the first question, if you come to the first question, then he's asking us find the real part of the dominant pole. The real part, the dominant pole is like that 0.48 plus j 0.64. Okay. So the real part is 0.48. So the answer for the first question will be 0.48. Then what is the magnitude of the imaginary part of the dominant pole? The imaginary pole magnitude will be 0.64. Okay, then my third question, from third question onwards your real problem will start, how we're designing the compensator. Now he is asking us What is the magnitude of the
Sir,
angle deficiency? Right.
small doubt, sir.
Yeah.
Sir, is
Yes.
it to be called dominant pole or desired pole, sir?
It is called dominant pole, not the desired pole, sir. Dominant pole because why it is called a dominant pole? Because this is a second order approximation. Because there are two types of pole. One is dominant pole, and another pole is called the non-dominant pole, or this is redundant poles. Redundant poles are something which are 5 time constant greater than the dominant pole, because in your step response, the dominant pole will decide the step response or the response of the system, not the far away poles. The far away poles will never or will significant contribution to the system response. They will not alter your percentage peak overshoot. They will not alter your system time constant. They will not alter anything. There is a minor change, okay, by having the redundant poles. But the dominant pole, if you change the dominant pole, then the dominant pole will change your rise time. The dominant pole will change your signal percentage peak overshoot, settling time, percentage peak overshoot. That all the things will be changed if you have altered the dominant poles. That's why whenever the root locus plot, if you have a root locus plot which is very far, uh, very nearer to the origin, means it is starting the origin and going to the right hand side, means that if it is going to the right hand side, then it will be system will be unstable. So that's why to make the system stable, we are adding some compensator like a lead compensator, or you are adding a zero. Then what will happen, then the root locus, whatever the branches, that is pulled down to the left hand side. If it will be pulled down the left hand side, then what will happen, the system stability will be increased. And that concept will be now here will utilize that how much magnitude of that pole, which means you can add a pole, you can add a zero which is nearer to the origin, or which you can add a zero which is far away from the origin. The far away from the origin, that has significant, does not have significant contribution. Okay, so always whatever the pole and zero you will add, that will be very nearer to the origin. So that is called a dominant pole, not the desired
Okay,
pole,
sir.
sir.
Okay, sir.
Okay, so this fast two, how I calculated the fast two. The fast two part I am not, because I am going to design my whole transfer function. But in that whole transfer function, you have the compensator part. I don't know which. In the question, he's telling us to design a lead compensator, but I don't know the exact zero and pole location. But they have given some data like what is the system omega n value and what is the zeta value. Okay, so from that, by taking from that, I know that this is my second order system standard equation. So I've just compared with that equation. If I compare that equation, then I will get some value S1 and S2. I know what is the formula. Then by using zeta and omega, I calculated S1 and S2. This S1 and S2 both are complex conjugate. Both can be a dominant pole, but for our solution of the question, I am taking a positive dominant pole. So S1 is called a positive dominant pole. So from the S1, he is asking us find the real part and find the imaginary part. So this is my dominant pole. Let's say it is called SD. Why I am denoting SD? Because in the throughout the lecture, SD Sarah has denoted SD dominant pole. So your SD, the real part is 0.48 and the imaginary part is 0.64. So the first two questions are nothing related to our compensator design. So now come to the third question. The third question is that he is asking us the magnitude of the angle deficiency. The overall system transfer function, if you go back, if you see, there is a 1 by s into s plus 0.5 and there is a GCS. I'm just drawing here the next slide. So this is a plant 1 by s into s plus 0.5, and here is a compensator which is called your GCS. So we know that these two system is now contributing our total loop transfer function. So now GCS into G of s, these two product, remember that these two product, because you are solving this question in time domain. Okay, time domain means you just imagine that there are two things in your mind. One is root locus is a time domain plot, another is your time response analysis by RH criterion. But RH criterion we are not going to deal here, we are going to deal with the problems by using root locus. So I told you that in the root locus, if this is the total transfer function, then there are two conditions you need to apply. Whether any point lies in the root locus will satisfy the angle condition, and if it is satisfying the angle condition, then find out the system gain. In the GCS there is some gain is there, so find out the gain by using magnitude condition. Okay, so these two things you know, that if any point lies in the root locus, you have to use angle condition, whether that point will be lies in the root locus or not. Because why? Because if I draw 1 by s into s plus 0.5, let me go to my MATLAB. Actually you'll feel how actually the system will be. Let me go to my screen. So is this screen is visible, this MATLAB window?
Sir.
Okay, so now you just
Yes,
see.
sir.
Now you see, I am just drawing because in the transfer function it is given 1 by s into s plus 0.5. Okay, so now you know that how a transfer function will be written in MATLAB, because on the numerator 1 is there, so I am just writing 1 here. Numerator, I am just taking a variable nr. Okay, so in the numerator let's say nr, and that value is be 1 because this is 1 by s plus 0.5. In the denominator there are two things, s into s plus 0.5. If multiply, this will be s square plus 0.5s, the second order equation. The second for s square, I am the just write down the coefficient. S square का coefficient 1 है, so you have to write 1. Then 0.5 into s, the second will be 0.5s, so this is the coefficient of s is 0.5, and there is no constant is there, so you write down the constant as 0. Then what if you write down the numerator and denominator, then what you do, first you have to write down the system. The system is nothing but transfer function. This is a function. TF is nothing but a function, and that will give the transfer function TF, nothing but nr into combination dr. You just write down these two variables. So this is the way you can represent your system. I am just calling that system as sys. This is a variable, whatever your name also you can take there, no problem. Next, what you are going to do here, if you want to plot the root locus of this system, then what you do, you just type down r locus. Okay, so if you write down r locus and that system,
नहीं
you
टूट घर पता है
you find out the RON. Let me save it. Now,
बुध गए
is my screen is visible? Is my screen is visible to all? Is this plot will be visible to all?
यस सर
Now you just see in this plot, this is the origin. Okay, this part is the origin where my cursor is, my mouse will be moving. This is my origin. Okay, so now this is the root locus plot, 1 by s into s plus 0.5. Here in this is the uncompensated transfer function. So if I coming back to my original circuit, if I find out the root locus of this, then it will be one pole will be located here, another pole will be located at 0.5. Then what will happen? They will come closer to each other. Both will become closer to each other, and they will have a break point. And after that break point, they will one pole will be moving the upward direction, another pole will be moving the downward direction. This is the root locus diagram. That also you can visualize that this is the pole, because this is a cross is showing here. So another pole is here on the left hand side, another cross is there. They are coming each other and they will be meet at this common point, and one pole is going in the blue, another going in the downside, the green. So this is the root locus diagram of the uncompensated network. Okay, so now the point is that what I'm going to show here. So if you want to show the step response, okay, if you want to show the step response also, then what will happen, you just write down. So if you want to find out the step response, so just write the command step. Okay, if you write down the step command of that system, then you can See the step response. The step response is coming something like that. Okay, so forget about this is not the exact step response. This is the step response of the system which is uncompensated. I will go to the compensated network. I'll show you how the step response will be. So for this system, you know that the root locus will be something here. Okay, so one pole is going upward direction, another pole is going downward direction, but we have to design a compensator such that such that what will happen, whatever the dominant pole location, that dominant pole should be lies on our root locus. That point you have to clear in your mind. You have a dominant pole. That dominant pole has to be lies in the root locus, because the dominant pole is the total system ka dominant pole, not the open loop transfer function ka dominant pole. This is the dominant pole of the total compensated network. So that pole has to be lies in the root locus. So what you can do, so for that, I don't know that there is something minus 0.4 and 0.6 at this pole will be here, but the root locus is coming here. So what you do, you have to shift this root locus towards the right side. So you have to shift this root locus towards the right, such that these two pole will be lies on that root locus. So that thing, how can you do that? That thing you can do by adding a compensator. So in the question they have given you to design a lead compensator. So know that for a lead compensator, the last class I told you how can you design the lead compensator, but for that you have to find out the angle deficiency. Okay, so in the question they have given the angle deficiency of some value. What is the value they have given? Uh, what is the magnitude of the angle deficiency? In the question they are asking us to find out. Okay. So, are you following? Because this is a little tricky part, the design of the compensator. From now onwards, every class will be like a design approach. You have to design your uncompensated network to a compensated network such that you have to meet the required specification. The required specification means in this question, the percentage overshoot, the settling time, like all this they have given in the question that I need this much settling time, I need this much percentage peak overshoot. You have to design a compensator. So you have to design either frequency domain, you have to design a time domain. So we are now dealing with time domain. So you know that for the both of the system, GCS into G of S, it has to be, the dominant pole has to be live in the root locus. It has to be satisfy the angle condition. You know that what is the angle condition? The angle of this total should be equal to minus 180. So angle of product of two is nothing but GCS plus G of S angle has to be equal to minus 180. Now you just tell me what is the angle of G of S at the dominant pole. These two all are at the dominant pole. Dominant pole I call SD. So first find out what is the angle contribution by this plant which is given 1 by S into S plus 0.5 at the dominant pole. So what you can do here, in place of S you have to write a dominant pole SD, and in place of S you have to write SD plus 0.5. Then put the value of SD. Okay, SD is nothing but your minus 0.4. What is the value of SD? Minus 0.48 plus J 0.64. This is SD
Six
and
four.
into SD plus 0.5. So whenever put SD minus 0.48 plus J 0.64 plus 0.5. So now for each of these term you need to find out the angle. What is the angle of individual term? Now tell me what is the angle of this first term. First of all, whenever finding out the angle, you have to see that in which quadrant this is lying. This is lying in the second quadrant because minus 0.8 plus j 0.6. This is in second quadrant. If one pole is lies in the second quadrant, then what is the angle? The angle is nothing but you can write 180 degree, because this is somewhere here. We are more focused on this angle, but the angle is always contributed from the real axis, positive real axis. So this would be 180 minus 5. This is, let's say, 5. So I can say this is 180 minus 5 is nothing but the imaginary part divided by the real part. So tan inverse 0.64 divided by 0.48. So you find out that angle. What is the angle contribution by that one? The first term. So what is the angle contribution by the first term? 180 minus tan inverse 0.64 imaginary terms divided by 0.48. This is the angle contribution by the first term. So what is that value? And similarly, what is the angle contribution by the second term? Second term is nothing but 0. This 0.5 and 0.48 will be 0.2. So, and both are positive now. Means this is pole will be lies on the right first quadrant. For the first quadrant, you know that it will be simply tan inverse imaginary part divided by real part. Imaginary part is 0.64 divided by real part is 0.5 plus 0.42. This will be 0.02. So now this is the first angle and this is the second angle. Add these two angles, how much this value will be? What is the angle, total angle of this? Are you calculating or I will tell the answers? So
It's
this angle will be nothing but, because you don't have calculator, so I am just writing down. This angle will be minus 215.07. This is the angle which is contribution by the plant GC. Okay, so I'm writing in place of this. This is the angle which is G of S at the dominant pole SD. But what is the equation? The equation is that GCS का angle plus G of S का angle, both दोनों का angle has to be equal to minus 180 because it has to satisfy the
minus
angle
180.
condition. So but here you need to find out what is GCS. GCS is nothing but minus 180 minus G of S angle. So this will be nothing but minus 180 minus G of S is nothing but minus 215.07. So it will be something minus 180 plus 215.07. So this will be 35.07 degree. So this is the angle which is contribution by your GCS. Okay. Now you can see your GCS is nothing but a compensator. If in the question he is not giving you the hint that whether it is a lead compensator or lag compensator, you know that lead compensator always contribute positive angle. As this angle is positive, then by default you know that whatever the compensator I'm going to design, it has to be lead compensator because the angle has to be positive. In the question, if suppose the angle will be negative, then by default, whatever the compensator are going to design, it is a lag compensator because lag compensator has an angle contribution negative. So that has to be clear that by looking at the angle, I can able to say that whether I'm going to design a lead compensator or whether I'm going to design a lag compensator. So now it is clear that I'm going to design a lead compensator. So for the third part, then the question third part, the magnitude of the angle deficiency. So how much angle deficiency is there, okay, to satisfy our angle condition? Okay, angle condition is minus 180, so that angle will be 35.07 degree. So this is the angle deficiency. That angle deficiency has to be provided by your lead compensator. So for the third bit, the answer will be 35.07 degree. Now come to the fourth question. The fourth question saying that what is the location of zero of the compensator? Now, after know that this phi d, the whatever this is the deficiency angle, from that phi d, now you are in a position that you need to say what is the location of the lead compensator pole and zero. Now, in the fourth and fifth bit, they are asking us what is the location of the zero and what is the location of the pole of the compensator. For the compensator, we don't have any data. Only one data is there, that we know that the angle contribution by this compensator is nothing but 35.07 degree. This is the only data you know. From this you have to find out, you know that this is lead compensator, so lead compensator pole zero location will be like this. So these two will be contribute a lead compensator. Okay, the zero will be close to the origin because to satisfy the angle has to be positive and the pole has to be to the left side of that zero to satisfy the lead condition criteria, because I told you this has to be GCS in the form of 1 plus TS divided by 1 plus alpha TS. Okay, this is the formula in the last class we have derived. So what you do, you know that if you design the lead compensator, so in the class, means in the lectures, you have gone through this diagram. Suppose this is your HD. Okay, you know that the HD location. So what you're going to do, you join this HD location from the origin. Okay, you have joined this at the position of SD. Now from that SD, you know that this is the angle that is, you know how you know that angle, because this is the angle theta. Theta is nothing but cos inverse zeta. Okay, because zeta you know from the question. So theta is the angle contribution by the dominant pole. Now you know that to satisfy the angle condition, you require a compensator that has to be provide some angle, positive angle. So 35.07. So positive angle means, let's say this is my something compensator. The compensator 0 will be located somewhere here, and this compensator has to be give a positive angle. Okay, this positive angle should be equal to 35.07. So you know that in a lead compensator not only a 0 is there. Whenever a 0 is there, to the left of that 0 a pole will be there. So now you place a pole also, because you are going to design a lead compensator. As soon as you place a 0, you have to place a pole of the compensator. Now this combination ZC and PC, okay, ZC is the 0 location, PC is the pole location. These two contribution should provide an angle which is 35.07 degree. So let me add someone which want to join. Is there any doubt till now? Is there any doubt what I'm going to say? Yes, everything is clear. Is there any doubt? You can
Yes.
stop me. Okay. So now you know that uh, till now this diagram is clear. This triangle which I made, why I made ZC and PC, SD in theta. Have you cleared this diagram? Okay, just go through once the lecture. Actually, it is in the lecture. Okay, so what now? First of all, you have to place your dominant pole SD. So I place my dominant pole here. I know that this join that from the origin. After joining that, you know that to the negative real axis, it's making an angle theta. This theta equal nothing but your cos inverse zeta value. This value is known because zeta is known. Then what is happening? I know that the angle deficiency is 35.07 degree. So these two combination, because you know that lead compensator is a combination of one zero, another pole. Okay, so I'm just placing that zero location here, and to the left of that a pole will be placed. So this is a lead compensator. So join to that ST. Now the total angle contribution by this PC and ZC should be equal to 35.07 degree. So that is represented by this angle phi. Okay, this phi, okay, this phi is something which is decide the location of your pole, because also it decides the location of your ZC. So this this distance from PC to ZC is decided by this phi. This phi is nothing but your 35.07 degree. So once you know that this diagram, you know, then apply sine rule to find out what is ZC and what is your PC. Okay, so you know sine rule, you have to just apply. So if you just, I'm writing down ZC. Okay, if this distance is ZC, ZC का opposite angle जो भी है, this angle, let's say x. Okay, so sine of x. Okay, so this angle in your uh, that is your lecture, it is given by gamma. Okay, so let me put that value, sine ZC by sine gamma. That should be equal to omega n, which value is known to us. This value is known to us, omega n. This distance is omega n. Okay, so omega n opposite angle, what is the opposite angle? This one, this angle. Okay, so let this angle is sine, because you know theta, you know gamma. So this angle will be 180 minus theta plus gamma. So it will be 180 minus gamma minus theta. So that is already derived in the, so you just, I am just giving how you can apply sine rule if you forgot the formula. So don't remember any formula, just apply the sine rule. Okay, so ZC, which value is known to you? ZC I don't know, unknown. So I put ZC by sine gamma. Gamma also I don't know. Okay, omega n I know, divided by sine 180 minus gamma plus. You know that sine 180 minus something is nothing but sine x. Okay, this formula I just apply here. Okay, so I'm just applying omega n divided by sine. Okay, 180 minus, take the minus common, So this will be plus, okay. So it will be gamma plus theta, because sine 180 minus theta is nothing but sine theta. So you just now from here, you just now in a position that you can find out what is the ratio of ZC by omega n. Okay, ZC by omega n you find out. This will be sine gamma, okay, divided by sine gamma plus theta. Okay. This is one formula you can derive from this triangle diagram. Other formula, what you know, likewise you have drawn for ZC, you have to also take the bigger triangle. Bigger triangle, why? Because I need to also find out the location of poles. So what you do, you just apply again sine rule. This will be PC. PC means the whole distance from here to here, and its opposite angle is this total angle. Total angle, okay. This will be how much? Sine gamma plus phi, and this should be equal to omega n, and the same you have to write out sine 180 minus. So what is that omega n? This angle, okay. This angle, if this is gamma and this is phi, then this angle also gamma plus theta, okay. This angle is phi, so now you can find out sine 180 minus gamma minus theta minus phi, okay. The total, all the angles will become here. Now similarly you have to find out what is the ratio of PC divided by omega n. So these two terms you need to find out from the sine rule of the triangle. You know these things, otherwise you remember the formula that is already in the classes, okay. So once you know, then what you're going to do, you just find out what is gamma. Gamma value is nothing but 1 by 2. What is that gamma value? This gamma value is nothing but 1 by 2, 180 degree minus theta minus phi. So first of all you have to find out from this value. You know that theta equal to cos inverse theta, okay. This phi value also it is given in the 35.07 degree. So now you use this equation and to find out gamma value. This gamma value will be coming some 45.9 degree, okay. Once you know that gamma value, then your question answer will be very easy. So use this formula to find out the gamma, okay. Then after finding out the gamma value, what you need to do, put in that formula which we have derived here, okay. Because once the gamma value is known, then theta you know, then you can find out omega n is known, then you find out ZC. Similarly in this formula, once the gamma value is known, theta you know, phi you know, then omega n you know, then find out PC, okay. So find out ZC and find out PC. So ZC is nothing but it will come around some 0.5817 put in the formula, and this value will be 1.1.002. So this is the location of your compensator pole and location. So you know that your GCS is now S plus 0.5817 divided by S plus pole location is 1.100. So this is your compensator, okay, transfer function of the compensator. Till now any doubt? You may have doubt, uh, because this is all our mathematics, okay. So but this way you have to solve the problem. There is no other way you can solve the problem. So better you just remember one or two formula. How? Just to remember gamma is, okay. Also to derive the gamma by using the similarity of the triangles, okay. Then you find out the sine rule to find out the exact location of the PC and ZC. Once the PC and ZC you know, then you can design the compensator. So no, GCS will be now in front of our screen. Once you got the GCS, then come back to the questions. The question is asking us to find out the what is the location of the zero. The location of the zero is at 0.5817. And what is the location of the pole? We have to put a negative sign because in the negative axis. The location of the pole is something minus 1.100. So this is the location of the zero and location of the poles. Now in the question he is asking us what is the gain Kc of the compensator. What is the gain Kc of the compensator? Once you have designed a compensator, you have poles and zero. You don't. He's asking us the gain. Gains. Let us add a gain value. He's asking us that gain value. How to find out the gain value? The gain value you have to again satisfy the magnitude condition. I told you once you have to angle condition is satisfied, then you have to find out the magnitude condition to find out the system gain. So what you need to do here, you know that GCS ka magnitude k, every term you find out the magnitude. S plus 0.5817 का magnitude divided by नीचे का magnitude 1.1002 का magnitude, but at which point at S equal to SD dominant pole, that should be equal to 1. Then what is the gain value? The gain value will be something SD के value इधर put कर लो, okay? Then it will be SD plus 1.1002 का magnitude divided by SD plus 0.5817 का magnitude. Okay, then put that SD value and find out the K equate to 1 to satisfy the magnitude condition. Then you will get some K value. That K value is coming around 0.7045. Okay, I have solved this question, that's why I am directly writing the answer. But you have to solve, you know the process how to solve, that's it. Already these things will be covered in time domain on the root locus part. Okay, only you just need to follow the process. How can I find out the system, uh, if system deficiency is there, then how can I able to find out the compensator transfer pole and zero location? After the poles and zero location is fixed, if I need to find out the gain of that compensator, then I need to use the magnitude condition. So at which point at the dominant pole concept, at the dominant pole, then after the gain k is there, then overall GCS will be how much now? The overall GCS is nothing but k का value डाल दो इधर 0.7045 into S plus 0.5817 divided by S plus 1.10 whatever this value. So this is our total GCS. Now GCS will be in front of you. You know G of S is nothing but 1 by S into S plus 0.5. Then you know the product of GCS into G of S is the total loop transfer function. This will be something 0.7045 into S plus 0.5817 divided by the two denominator. One is S into S plus 0.5 into S plus 1.100. This is the overall transfer function of the system. Now after you know the compensator, this is the loop transfer function, open loop transfer function, open loop transfer function. Till now, any doubt, everyone? Anyone? Is there any doubt? This is simple mathematics, okay?
No,
Because
sir.
yes, ma'am, are you going to say something? Is my voice is clear or not?
Okay.
Actually, voice is not coming from your side. Is everything is clear? Just one confirmation. I need one. Okay, no doubt. Thank you, ma'am. Okay, so see, means in the question, why you are reading this? Why you are reading this? Because we have an uncompensated plant. Okay, whenever you have uncompensated plant, there is something disturbance will come. Then what will happen? Your system response will be something different, which is not equal to our desired response. So what? To find out the desired response, we are designing the compensator. So the compensator, it can be either a lead compensator, lag compensator. It can be a controller, also called compensator. So don't be confused that PI controller, lag compensator. So all are related. So, but in a specific, we are reading this week 8 is related to design of the lead compensator by using root locus approach. So I'm designing a lead compensator or designing a lag compensator or designing a lead lag compensator, whatever. But in the whole process, you have to understand that Once a plant you have given, then you see the plant and see the question which what is the things need to be asked. So like this question number, you go to the questions. So in the questions now you know the gain. Once the gain is known, this question number 7 is the maximum overshoot percentage of the compensated system. This thing you cannot find out. You cannot find out by using any formula. Okay, you can find out. Now you can find out. But this is the percentage overshoot of the compensated system. To find out the percentage peak overshoot of the compensated system, you have to find out the whole transfer function. Now, your whole transfer function, you cannot find out this by using your open loop transfer function. If you find out, suppose, the question number 7, what is the question? Find out the maximum overshoot. Okay. So don't say your answer. Don't say your answer. Because you know that percentage peak overshoot formula is e to the power minus pi zeta divided by 1 minus zeta square. Because zeta is given in the question to you. Okay. What is the value of zeta is given in the question? What is the zeta value? 0.6. So if zeta value is 0.6, if you put this value, you get a percentage peak overshoot, which is incorrect. Remember. Just put and tell me. Just put and tell me what is 0. If you put 0.6, e to the power minus pi into 0.6 divided by 1 minus 0.6 square. What is the value? Can anybody confirm me? What is that value? Anyone is solving this? Put zeta equal to 0.6 and find out percentage peak overshoot. Nobody is doing. Guruman sir, are you there?
Yes, sir. Yes, sir.
What is the percentage peak overshoot now? Are you following? Because you don't have doubt today.
Yes, sir. Yes, sir. Following, sir.
What is the percentage peak overshoot? If you put this formula, you will get some percentage peak overshoot, sir. But I don't say this is the accurate answers. Okay. So for accurate answer, what you need to do, you find out the closed loop transfer function. This closed loop transfer function is this is what I have written here, 0.7045 into this, and the denominator is this. Okay. So I'm just writing down here. Closed loop transfer function is nothing but G in. Okay. The closed loop transfer function is nothing but, sorry, this is the loop transfer function. Okay, this is a loop transfer function. For closed loop transfer function, what you need to do again, GCS into G of S divided by 1 plus GCS into G of S. You have to do this, okay, to find out the closed loop transfer function. Then in that closed loop transfer function, you find out omega n and then 2 zeta omega n, you compare. After that, you find out what is your omega n value and zeta value. After that zeta value, put that zeta value in this formula, you might got a answer which is close. Okay, but let me solve this problem by using MATLAB. Percentage peak overshoot, I told you how to find out. You just find out the loop transfer function, then find out the closed loop transfer function. Then this closed loop transfer function is something. Let me find out the closed loop transfer function for you. This closed loop transfer function is nothing but, let me find out for you because otherwise it will not be clear. GCS into G of S is something I got K into S plus 0.5817 divided by S into S plus 1.1002 and S plus 0.5. This is my open transfer function. K value, we find out that this is 0.7045. Okay, so let me approximate it. Okay, so let me write down like this. 0. I'm writing 0.7. This will be 0.5817. You just write down for simple calculation. It will be 0.5 divided by s into s plus. Write down this is 1.1 into s plus 0.5. Okay. Then what you need to do? Find out the closed loop transfer function. First to multiply. First to simplify further it. This will be 0.7 into s plus 0.7 into 0.5 is 0.35. Then this value solve. After solving this value, how much this value will be coming? So this will be coming like this, SQ plus 1.6 times of s square plus 0.55 s. This is the numerator part and this is the denominator part. But this is your GCS into G of S product. But closed loop transfer function, what you need to do, whatever the denominator, just add in the, whatever the numerator, you just add in the denominator. So write down directly because the unity feedback system, that's why 0.7s plus 0.35 divided by s cube plus I'm adding this 0.7 1.6x square, this 0.55 is and 0.7 that will be get added off, that will be how much, this will be 1.25 times of s plus again this 0.35 is there, this 0.35 is getting added there, so how much that value will be, this 0.7s, this will be 0.7s, right? Okay, so 0.7s and 0.55s will be 1.25s. Okay, and this will be how much, this will be 0.35, but this constant is get added up. So this is the closed loop transfer function. Till now any doubt how I find out the closed loop transfer function? So now after you find out the closed loop transfer function, then you equate, where is that omega value is now, omega, this is the third order system. Now you see, this is third order system. So you don't know for a third order system how to find out the percentage peak overshoot. So that's why this question you cannot solve numerically. You have to go to the MATLAB to find out the percentage peak overshoot. Remember that in the question, if you get a third order system like this and they're asking percentage peak overshoot, then you have to use MATLAB. Otherwise, there is no formula with you to find out the system percentage peak overshoot. Now, this equation I'm putting in MATLAB and I'll show you that what is the percentage peak overshoot. Okay, so now come to my screen here. So I have already written this one value. See, this part, this nr1 is the uncompensated system transfer function with the planned actually which is given in the question 1 0.5. Okay, so this is 1 by s into 0.5 s, this is the, so this I'm calling system 1. Similarly for the system 2, you see that the numerator having a coefficient of s and constant, so s is having, just take the coefficient 0.7 and 0.41. so why I've taken here 0.41, because this value I have multiplied here 0.7 and 0.5817. So if you multiply exactly the value, then this is not 0.35, this will be 0.41. So that's why this will be 0.41 only. This will be 0.41 and this value will be 0.4. Now you see the coefficient here 0.7 and 0.41. 0.7 and 0.41 I have written in the numerator 0.7, okay, and 0.41. It is clear? And this screen will be visible to you?
Yes, sir. Visible, sir.
Okay, then come to the denominator. To go to the denominator, then you see how much value I have written here, the coefficient, just to see the coefficient. one coefficient is 1, 1.6, 1.25 and 0.41. So these four values you have to write in a matrix form. So write down that four values in the matrix form. So 1, 1.6, 1.25 and 0.41. Then what you do, you just write this as a transfer function, numerator comma denominator. So that will give you the transfer function. I am calling it a variable system2. Then you are interested in to see what you are interested in to find out the step response of the system. Because why? Because from the step response we are able to find out the percentage peak overshoot. So what I did here, forget about the root locus, this value, just I am just commenting out it. Okay, so individual you can see the step response, individual you can stay the step response, but what I do, I am just making the two figure into a single figure. So I'm just plotting that in a single MATLAB figure. So I'm putting a command figure. Then I want to see both the response simultaneously. So what you do, you want to see the step response, so put a command step. Step is nothing but a function. Inside the function you are defining your variable. Your variable for the first transfer function is system1, and for the second transfer function it is system2. So system1 and system2, if what is this B and R, these are the colors. You want to see in which color your system, these two plots will be plotted. One is in the black color, another is in the red color. Sorry, B is for the blue color and R for the red color. Then you are using some legends. Okay, legend means which one is system 1 and there is system 2. Title of the response, X label, Y label, this is as per your wish. If you want you can keep, otherwise don't keep. Then what is called, then compensated system is system 2. Remember, after this is the first one which is given the question. This is the uncompensated system, and system 2 is a compensated system. So I am interested to find out the percentage peak overshoot of the compensated system. So for that, what you need, you have to use, in a step response you have to use the function to find out the step response of the system. So what is that command? The command is that step info. Step info is a command. If you put inside, it is generally a function to find out the step response. So if you use this step info command, then you are in a position to find out anything on the step response. Like you can find out the overshoot, you can find out the settling time, you can find out the rise time. So just in that step info, for which system you want to find out, let's say for system 2 of the compensated system, I want to find out the step info. Then I am saving that step info data into step info variable. So I keep in a step info variable. Then that step info variable, what you need to find out, just if you find out the overshoot, then put a dot overshoot. If you find out the settling time, then put a dot settling time. These are the commands with respect to the step info, what you need to exactly see in the step response. So after your step info will be there, that step info I need to find out the overshoot. So that is a command called overshoot. So step info dot overshoot, then that will give you the percentage peak overshoot. Similarly, if you find out the settling time, then step info dot settling time, then that I need to store in a variable settling time. Then what I did, I need to display that variable. So display what? Percentage peak overshoot and settling time of which system. Let's go for system 2. I just wanted to calculate for system 2 because that is a compensated system. Then I want to convert that numbers into string because I want to see in a string format in the percentage and in settling time in second. If I run this program, then what you need to do, you just see that this the plot is coming to you. Now you can see for the uncompensated system, this is the blue line for the uncompensated system. Okay, for the uncompensated system you can see that how that system will vary and reaches the steady state. But in a compensated system, whenever you putting a lead compensator, now you see the percentage peak overshoot is drastically reduced. Now we can see this one value is step response, one value is step response. Now from 1 to 2, the peak, there is no overshoot. See, there is no overshoot is, but in the compensated system, if you find out the system overshoot, so this much height from 1 is how much. If you want to see that value, then how much that value it is showing in my MATLAB, the percentage peak overshoot is 11.80%. So The answer for the seventh question or eighth question, seventh question is 11.8%. And what is the settling time? The settling time is 7.4 seconds. So in that way, you need to find out the percentage peak overshoot and the settling time. Anything, rise time, peak time, everything you can find out by putting the appropriate command. Okay. So now you see that what is the answer for the seventh question is 11.8%. So in that way, you need to find out that what is the percentage peak overshoot for the compensated system. So what is that value? This value will be something 11.8 percentage. Any doubt how I can, because it's the third order system, you cannot find out the percentage peak overshoot. So you have to use the MATLAB by default. So 11.8% is the percentage peak overshoot. That also you can see from the plot. If you see the plot also, you can able to see that. Just a minute. You can see this much height is something around 1 to 1.18 something. So that height is from 1 to 11, 1.18. So it is 11.8%, right? So that way you can, up to 7% everything is clear. In doubt, how can you find out the percentage peak overshoot? Settling time, I have just given settling time also in my command code. You can also find out rise times, okay, delay time, okay, anything you can find out by using appropriate command. Any doubt? Because I saw the assignments of question number, I saw the assignment of question number week 8. Because in the week 8 assignment, if you have gone through, then you can see that it is also suggesting that you can use the MATLAB function to calculate the percentage peak overshoot and all the values. Also you can use MATLAB, okay, settling time, everything you can use MATLAB. Okay, so whatever the transfer function is given, just write down the transfer function. No need to solve anything, no need to solve anything, just
Sir,
to, yeah, yes ma'am.
sir, give me the answer for settling time, sir.
The settling time is coming, ma'am. Uh, just a minute, ma'am. Phone is there. The settling time is 7.45, 7.4 second.
Thank you, sir.
Okay, ma'am. Okay, but also if this is
Okay, sir.
this is for system 2 I have written. If you want to use what is for system 1, system 1 is for uncompensated. You also put 1 year, 1 year. Okay, in the step info you just write down system 1. Then okay, just take a screenshot of this code and try this code by yourself, how to find out it. Okay, let me come to my next question. The next question is that question number 8. Question number 8 is that for a larger angle deficiency, okay, a single lead compensator is replaced by two lead network. Okay, sometimes what happens, sometimes what happens, uh, this angle contribution by your lead compensator is 35.07 dB. Okay, suppose a plant is very very large, okay, and you are not interested that I am not using only, because sometimes, because these are all mathematical calculation, but in the practical what you need to do, practically you have to design the lead compensator by using R and C values. Okay, so I just showed you that this is R value and this is C value. Okay, this is some this is the lead compensator. So practically you need to design these values, R and C values. Sometimes these values are very very large. Okay, so what do you need to do, you have to use cascaded. So this 5D 35.07, suppose you have a resistor capacitor that will not able to provide this much angle, then what you need to do, you have to use cascade connection. You want to divide this lead compensator into two lead compensator. Okay, two lead lag compensator, sorry, not lead lag, this is lead, this is also lead compensator. Okay, so this is one, this is two. It means the angle contribution of this 35.07 is now not coming from one compensator, is coming from two compensators. Okay, so in that case, if you go to the question number 8 and read carefully, then what is he saying? He's saying that for a larger angle deficiency, a single lead compensator is replaced by two lead network. Okay, lead compensator, considering both the lead network to be same. Now he's saying that both the lead network is same. It means whatever the diagram I draw here, this diagram R and C values are same. Okay, means it is ideally same. You have to design two lead compensator which are ideally equals. Then he's asking us for the same problem, whatever the problem is given to us, what is the location of zeros of the lead compensator? What is the location of the zeros of the lead compensator? Lead compensator. So what you need to do here, are you saying it is ideal, then what is that? This total angle will be now contributed by this one and this one. It means if 35.07 by 2, you just do by 2, then it will be something around 17.53 degree. The 17.53 degree will be contributed by lead compensator 1, 17.53 degree, also lead. So now whatever the process you did till now, you have done for 35.07. Now you do for same for 17.53 degree. Okay, this is your now angle deficiency. This is the angle deficiency of the second lead. So now he's saying that for this lead compensator, you find out the zero location and the pole location. So you know how to find out. Use that formula gamma. Okay, in that gamma, this is the formula 180 minus 5 minus, okay, what is that formula? Gamma equal to 180 minus 5 minus theta. Okay, but here is now theta is fixed, but your phi is now getting half. Okay, here you just put 17.53 degree. Here this is 53.67 degree, it is fixed. Now you find out gamma value and find out ZC and ZP value. Okay, I am not going to solve. I just make you understand that how you are going to solve this problem. Next, come to the next question. The next question is something. What is the location of the poles of the lead compensator? Once you know the zero, then also you know how to find out the pole location. Now come to the question 10. The question 10 is that the maximum percentage overshoot of the lead compensator. Then once you design your compensator, you now find out the open loop transfer function, then the closed loop transfer function, then you put that closed loop transfer function into MATLAB, then find out the percentage peak overshoot. Okay, so these three problems I am going to as a homework for you. Okay, you have to do by yourself, because it's nothing but only you have to make that phi value half. 17.53 put, find out gamma. After finding out the gamma, you know how to find out ZC and ZP. Once ZC and ZP you find out, then this will be ZC divided by ZP. This is a compensator is fixed, then K value find out. After that you find out the open transfer function. After that you need to find out the closed transfer function. Then from the closed transfer function you need to put in the MATLAB code to find out the percentage peak also. That's it. Okay, this part is all related to question number 1. So all the 10 question you need to solve by yourself. Okay, uh, next let's go to the second problem. The second problem, there are 5 questions. So this is the design of a lag compensator, not a lead compensator. This is the design of a lag compensator. You just read the question carefully. This is a plant is given, which is the third order equation. Then it is desired that the compensator's system meets the specification. Here this kV is given. Kv is the velocity error coefficient, but the velocity error coefficient is given 5.45. Okay, and the maximum peak overshoot is given 1.52 percentage, and the settling time is given, I'll assuming a 2% tolerance. 2% tolerance means settling time is nothing but a 4 times of time constant, which is given 5.03, okay, seconds. These are all the values, the data which is given in the question. Now he is asking us to find out the dominant pole. You know how to find out the dominant pole. I will solve now. Second problem, if only a gain adjustment gives a desired transient performance, what is the value of K? Okay, he is saying that you have to design a compensator where you have to design a compensator where you can only vary the gain. Means compensator is not required. You just vary this gain. This by varying the system gain, you have to uh, uh, okay. We have to, by varying the system gain, we have to as reach this performance kV value, MP value, settling time. Means only by varying this K value, you have to reach at this all the desired parameters. Then what is the value of K, which will satisfy kV equal to 5.45? What is the value of K which will satisfy MP equal to 1.52%? What is the value of K which will satisfy your settling time 5.03? So we have to find out that what is the value of k. He's not asking anything, he just saying that only by gain adjustment, what is the value of k, that will give you all the uh, response. Next, then the third part, he's asking us the velocity error constant of the gain compensated system. Once you find out the gain value, then you have to again find out the velocity error constant. Okay, and to satisfy the total velocity error constant of 5.45. So let's go one by one. How can you able to solve these questions? Okay, so how to solve that questions? Let me go some slides. Uh, Let me put some blank cell. Now you see, this is question number 11. So g of s is something k divided by s into s plus 2 into s plus 4 is given to you, and kv's velocity error constant is given 5.45, and your settling time is given 5.03 second. Okay, and your percentage peak overshoot is given how much? 1.52%. Okay, these are the three values is given.
1.5.
These are the three values is given for this question. He is asking us find out the dominant pole location. So first question, you have to find out the dominant pole. So what you need to see, percentage peak overshoot, you know the formula, e to the power minus pi zeta divided by 1 minus zeta square. From here, put the value of percentage peak overshoot is 1.52, 1.52, okay, percentage, so divided by 100. So, and if from here, zeta is only unknown, so find out that value 1 minus zeta square. Okay, so this zeta will be coming something 0.799. Zeta is coming from 0.799. Then once the zeta is known to you, settling time, you know that 4 divided by zeta omega n. Okay, once you know zeta, then you find omega n. How to find out the omega n value? You have to find out the omega n value because settling time, you know, 5.03. So from here you find out omega n, which is coming 0.995. So omega n is coming 0.995. Okay, then the dominant pole, you know that the formula will be minus zeta omega n plus minus j omega n into 1 minus zeta square. Okay, put in that formula, you will get the dominant pole is something minus 0.795 plus minus j 0.598. These are the dominant pole location. Okay, so once you know the dominant pole, the real part and the imaginary part, you take the positive dominant pole for further calculation. Once you know the dominant pole, then he is asking us, uh, let me go back to the question. After the question 1 dominant pole is over, then if only gain adjustment is there, you have to find out the value of k. Anything I told you that if you find out the gain value, you always require to use magnitude criteria, magnitude condition. Okay, to satisfy the magnitude condition, at which point are the dominant pole location. So do that. So what you need to do here, in this formula, in this you have to find out the gain value, apply magnitude condition at the dominant pole to find out the gain value. Okay, that thing you can do. If you do that, then this gain value k is to be coming around, k value it should be 4.36. This k value would be 4.36. This is the second question answer. Okay, so this is the question number 12. How to find out the system gain? You have to use the magnitude condition, equate the transfer function, add the dominant pole to 1, and then find out the k value. Okay, then after what the third question is saying, the third question is saying that once the system once this everything is done, you need to find out the velocity error constant from the question number 12. Okay, okay, so what, how can you do that? Let me add a slide here. So you know that question number 13. So let's say velocity error constant, you know the formula, limit s tends to 0, s times of g of s. Okay, So you know that g of s, k value, what is that k value? K value is 4.36. Okay, divided by s into s plus 2 and s plus 4. Okay, this is the this is the g of s. You take the limit here. This is the g of s. Okay, just I'm writing here, limit s tends to 0, s into g of s. Now s's get cancelled, so what is that value? 4.36 divided by, if you put s equal to 0, that will be 8. Okay, this will be the kV value. So kV value is nothing but k divided by 8, which is coming around 0.545. So your velocity at a constant will be 0.545. Okay, next let's go to the next question. Okay. Next, what is the value of the beta? This is beam, this is beta value. Okay, what is the value of beta? Assuming we design a lag compensator to achieve the desired desired kV is 5.45. Okay, what is the desired kV? Desired kV velocity at a constant is given in the question 5.45. But in our in our system, by varying the k value, we get the kV value is something around 0.545. Okay, then you know that if you have gone through lectures number third, okay, lectures number third, this beta value for the lag compensator is nothing value kV, which is desired, which is given the question, divided by kV, which is on compensated network. Because we are not using compensator till now, because only we are varying the k value, we have got a kV value. So this kV is nothing but an uncompensated network. Okay, so I'm writing kV, which is uncompensated. Okay, so this beta value now you can find out. kV desired is 5.45 divided by 0.545. So if you do the ratio, you will get a beta value which is around 10. Okay, so now you know that for a lag compensator, the beta value is 10. Beta is nothing but, for the lag compensator, I am saying like this. Okay, don't be confused, because 1 plus Ts divided by 1 plus beta Ts now. This I am calling beta. And this beta value, we know that for a lag compensator, it has to be greater than 1. So we got the beta value is now 10. Okay, now this beta is known to you. This value is now 10. this is this is my lag compensator transfer function. 1 plus ts divided by 1 plus beta ts. Beta, beta is nothing but 10. Now from here you need to find out the last bit. What is the last bit is there? What is the value of beta? Beta is 10 now. What is the pole of the lag compensator? Okay, he is given in the question that suppose the pole location of the lag compensator is at 0.01, then what is the location of the zero of the compensator? Pole location is given to you. You just need to find out the zero location. Very simple question. Pole location is given to you. See which one is the zero. Zero is this one. So zero means 1 plus ts को zero कर दो, तो s you will get minus 1 by t. This s location is nothing but the location of the zero. Similarly, for the pole location, you need to make 1 plus beta ts equal to 0. Then find out the s value. S value nothing but minus 1 by beta t. Beta okay, pole location is given to you. You first find out the time constant here. Pole location is given to you. What is the pole location is given? Minus 0.01. Minus 0.01 is given to you. Beta is 10. So t value find out from this equation. So t value is coming around 10. Okay, so if t value is coming here 10, then put that 10 value here, minus 1 by 10. So this will be minus 0.1 is the location of the zero. He's asking us the location of the zero. So I think it is clear to everyone.
Yes, sir.
Okay,
Clear, sir.
just go through the lectures once, because this part is related to design of a compensator, lead compensator, lag compensator. But most of the things from the understanding of your time response and root locus and all the formulas related to that time response. So go through once and solve this question. Go to lectures, and what are there are some There are some exercise questions I have solved. Try to solve that and solve. Watch this video again and solve all the question and you try to solve your assignment. Okay, it will be easy now how to solve your assignment. Okay, so these 15 questions I have just similar to your assignment questions. Try to solve your assignment and if any doubt you just ask me in my WhatsApp. Okay, let me give my number, so no problem. So I'm stopping here. Okay, just watch this lecture again. If you have any doubt then just call me, otherwise message text me. I'll clear a doubt. Okay, so I'm stopping here. Okay, for today. In the next class also we'll do the same thing by using frequency response analysis like Bode
Thank
plot.
you so much, sir.
Okay, okay ma'am. Okay, no problem.
Thank you, sir.
Yes sir. Okay, good
Okay,
night
sir.
sir.
Good night, sir.